You're listening to MedX, the Medical Extrusion Podcast, presented by U.S. Extruders. Extrude with confidence, custom extrusion equipment designed for you and your application.
Welcome back to the MedX Podcast. Today's guest is Basker Lalgudi, Business Manager for High Performance Medical Polymers at Evonik Corporation. Evonik is one of the world's leading specialty chemical companies, and their portfolio includes the VESTAMID series of nylon 12 and PEBA materials that are used for extruding medical tubing in minimally invasive catheters and balloons. The focus of our discussion today is related to co-extrusion and reflow of Evonik's VESTAMID bondable PEBA directly to Daikin's EFEP fluoropolymer for creating two-layer structures with a lubricious inner layer and a bondable outer layer. Before we get started, I'd like to give our listeners an overview of thermal bonding of similar and dissimilar materials. And when I say similar and dissimilar, I'm talking about similar chemistries. So the first one is the direct bonding of similar materials. Perfect example is PEBA. PEBA is a copolymer with a nylon 12 hard segment. So PEBA will co-extrude very well with nylon 12. You see some of these co-extrusions used in balloon applications. Another example is medium density co-extruded with low density polyethylene. Very similar chemistries. An example of the co-extrusion of dissimilar materials is a PTCA catheter. Now, this is a common tri-layer structure used in med tech with a high-density polyethylene inner layer for lubricity and a PBAX or sometimes nylon 12 outer layer. And because these two materials are dissimilar, it requires a adhesive layer, very thin, maybe 1/1000th of an inch wall thickness layer of Plexar, for instance. So this is an example of dissimilar materials. Now, fluoropolymers are very difficult to bond with because they have extremely low surface energies. So anytime you're going to bond a polymer to a fluoropolymer, it requires an extra step, whether it's inline or offline, meaning it requires chemical etching or plasma etching to activate the surface so that you could bond other materials such as a PBAX or nylon 12 or maybe even a polyurethane to it. So I just wanted to give you that quick overview as we start our conversation about co-extrusion. Basker, I'll take the liberty to provide some information about Daikin's Neoflon RP5101 EFEP, which is a copolymer that was developed for extruding thin wall tubing. Although it's not a fully fluorinated fluoropolymer like PTFE, FEP, or PFA, it has similar mechanical properties as other fluoropolymers, such as a low coefficient of friction, chemical resistance, and very good barrier properties, with the additional benefit in this case that it can be bonded thermally with other materials without an adhesive layer or chemical etching. It is a fluoropolymer, like I said, and it does require on the extruder special construction, high nickel content to avoid corrosion. Basker, thanks for taking the time to come on the MedX Podcast today.
Well, thank you, Steve, for having me on your podcast. And thanks for this great opportunity to present a very unique, one-of-a-kind technology for the world of catheters and medical device industry in general. So thank you.
Absolutely. I'm real excited about this conversation, of course, just because it's related to extrusion and medical device and catheters. I gave a background of the difference between co-extruding or bonding similar materials, dissimilar materials, and a little bit of background on Daikin's RP5101, their EFEP. So now that we have that background behind us, if you can share with us, Basker, the work that Evonik has done to develop this modified PEBA that will bond directly to the Daikin EFEP, either during co-extrusion or reflow.
Yeah, absolutely. So, Steve, historically, if you look at the construction of the catheters, multi-layer catheters, whether it's PTCA angioplasty or guide wire catheters, you have fluoropolymers on the inside for lubricity, and then you have VESTAMID PEBAs on the outside for flexibility and kink resistance. Now, because those two chemistries are very dissimilar, they're not compatible to each other. The process that's been used in the last 15 to 20 years involves multiple steps, 6 to 7 steps actually. There is chemical etching involved, there is mechanical etching involved, there's usage of expensive adhesives, and it's time consuming. It requires a lot of resources, and it costs energy. There is energy cost there too. So what we have done, what Evonik has done is, because the industry has been looking for a technology that can simplify the whole process, and how do we convert from multiple steps into a very simple process to make multi-layer catheters? Industry has been looking for it, and Evonik has been working on this for at least 5 years, and we didn't succeed in the beginning. We went through a couple of versions, did not succeed because those two products, fluoropolymers and VESTAMID PEBA, they're two separate chemistries. Now, we have finally succeeded. We actually went back to chemistry level. So we had to do the modifications at the chemistry level. So the new bondable VESTAMID can be extruded directly on top of fluoropolymers, something like Daikin EFEP, let's say RP 5101 grade, in one step. You don't require adhesives, you don't require any surface treatment, and it reduces the amount of resources and the cost. So the technology is being tested, it's being commercialized now, and we are very proud of the bondable VESTAMID products for the multi-layer catheters.
Excellent. Basker, when you look at minimally invasive catheters or delivery systems, typically you have the stiff or harder durometer polymer on the proximal end and soft lower durometer material on the distal end, maybe from 72D down to 25, 35, 40. Talk to us a little bit about the durometer ranges that are available.
Yeah, so our offering in the bondable category is anywhere from 40 Shore-D up to a 71 Shore-D. Today we have standard VESTAMID products like ME40, ME55, ME62, and ME71. Those are standard VESTAMID products that's been used for 20 plus years. We have kind of replicated the same hardness in the bondable category too. So we have ME40B, B is for bondable, ME55B, ME62B, and ME71B. So just to answer your question, we have hardness levels from 40 Shore-D up to a 71 Shore-D that can be used in direct straight catheters or complex catheters.
Okay, excellent. Basker, when you're co-extruding similar or dissimilar materials, two of the factors that will guide us to success in a multi-layer structure are the processing temperatures, right? They need to be similar. We think of fluoropolymers being high temperature, and if the temperature of the fluoropolymer is too high, it'll burn the bondable material. And the other factor is really important is viscosity, the viscosity levels of both materials. Viscosity, a function of temperature and shear. And if we're going through two materials flow paths through a coax die head, and if the velocities are different because of a mismatch in viscosity, you'll have interlayer instabilities and poor quality. So what can you share about, these very important temperatures and the viscosity levels that are needed for success?
Yeah, that's a great question, Steve. We actually took that into consideration when we developed this product. If you look at VESTAMID PEBAs, it's based on laurolactam, which is the hard segment, and a co-monomer, which gives the softer side of it. It acts as a soft segment. We used similar structure. We did not move away from our standard VESTAMID chemistry, but we made that bondable to the fluoropolymers. So when it comes to processing, when it comes to extrusion machines, and when it comes to the process conditions, you don't have to change anything. The viscosity of the product, the physical attributes of the product, the mechanical properties of bondable Vestamid are very similar to the original Vestamid care products. So you can use the same machines, same process conditions, and the co-monomer that we use in our Vestamid care products in general, it provides a lot of guts. Fluoropolymers are processed at very high temperatures. They melt around 195 to 200 degrees Celsius. They're processed around 275 to 290 degrees Celsius. So the Vestamid care PEBAs they use, you have to make sure they don't degrade, and you have to make sure they don't disintegrate. And that's what a Vestamid care product does. It has a lot of guts built in, and we don't have to worry about any effect on high temperature polymers like fluoropolymers on the viscosity and the properties of not just the bondable Vestamid care, but also the original Vestamid care products. So nothing is changing there.
Okay, very good. I know that you have some interesting data to share on the peel strength of the two materials that are bonded together during co-extrusion. So I'll let you talk a little bit about that, and I'll share this slide that you provided. Very interesting.
Yeah. Thanks for presenting this information. So we actually produced catheters at our Allentown Medical Center of Excellence. We have dedicated extruders to make the products, not just for R&D purposes, but also some advanced design purposes as well. Now, if you look at the data here, the curve here, on the left side, you have ME55B, and on the right side, ME40B. So we took a couple of grades. The black flat line, that's for non-bondable version. And then the purple line, the spike you see, that's for the bondable version. You can see the bonding strength or the peel strength of the bondable Vestamid care is 78 times compared to the standard PEBA products. Now, we have made a lot of catheters, and we also had a very big global medical device company came to our site. I don't want to mention the name, but we ran a lot of trials one full day, and they were super impressed with the bonding strength of the product and the quality of the catheters, multi-layer catheters. We were trying to separate them manually with bare hands. You can't separate them. You need to have some kind of Instron machine to separate those two layers. That's how good the bonding strength is, because it's done at a chemistry level. There is no expensive adhesives. There is no treatment applied. It's one-step co-extrusion, bondable Vestamid care on top of fluoropolymers like EFEP, Daikin, RP5101, and that's the result you see. These are actually real test data for 40B and 55B, and you would see something similar like this for ME62B and ME71B.
Okay, excellent. That's really good data. In a composite catheter shaft, there's usually a reinforcement in between the lubricious inner layer and the outer bondable layer, soft layer, whether it be a coil, a braid reinforcement. More and more hypo tubes are used today. In addition to co-extrusion, this data here on the peel strength is incredible. Have you also tried to laminate or reflow these two materials together?
Yeah, so we have done some work with the reflow as well, and we're able to make high quality catheters, excellent bonding strength, and we are actually working on making thinner layers now. How to reduce, because real estate is very important when it comes to catheters, and when it comes to dimension, we have tried different dimensions, different thickness level, and we're always constantly looking to improve the processability of the product and even the thickness of the material. So to answer the question, yes, we have done some work on that.
Okay. Just to continue what you talked about, needing more real estate, right? You were at the MPP East in November, and one of the highlights of the catheter panel was, profile is king. Wall thickness is king, because we need more real estate inside the inner lumen for wires, devices, drugs, fluids. What can you share about so far to this point, some of the samples that you made, the size and the wall thickness in particular?
Yeah. So we're a little bit spoiled in that category. So we have a dedicated medical extruder for bondable Vestamids and even standard Vestamid care products. We have been able to make different diameter ID and ODs. I would say if you want me to give a range, I would say an OD of 2.4 mm and an ID of 2.2 mm. When it comes to the thickness of the product, anywhere from 50 microns and 100 microns. Like I said before, we're actually working to make, trying to fine tune the process to make it a thinner, layer of adhesion. So we're looking into 25, 30 microns as well.
Okay. Yeah, I think actually that the inner EFEP layer is the one that you really need to thin up, right?
Yeah, and
To,
there's a very good picture of over there. I mean,
Mhm.
you can see the actual products we made from our dedicated extruder, ME40B, all the way up to ME71B. That's 40 hardness, 55 surety hardness, 62 and 71 surety hardness. On the right, so the top right, that's the actual separation. You can see using an Instron machine. You just can't separate them with bare hands. You have to use a machine to separate them. And at the bottom, you'll see the two faces, the Daikin RP5101 EFEP and the VESTAMID Care MEB bondable grades. Those are the two the faces. I mean, you can see the adhesion
Mm,
at a chemistry level there.
yeah. Oh, good product, good tubes, good job. Um, I see there's images here. So are there samples that are, if somebody's interested further, can you send samples if somebody's interested in that?
Yeah, so the product is commercial. If anyone is interested in quantities to test the product, run some tests and trials, please contact us. And we have resin products, ME40B, ME55B, ME62B, and we also have some catheter samples we have made on our extruder. So if you want some catheters for show and tell, we have them too.
Okay, great. Um, I assume that the bondable grade of the VESTAMID PEBA is similar in biocompatibility and sterilization.
Absolutely. It's medical application. These products were designed and commercialized for medical applications. Temporary contact, less than 30 days in vivo application. So all of our care brand products, Vestamid Care and bondable Vestamid Care, they have USP Class 6 clearance. They have, from a biocompatibility standpoint, they have ISO 10993 clearances as well, and FDA. So any products we supply into medical applications, we make sure we have all the right clearances. And yeah, so we have the regulatory approvals, and also from a sterilization standpoint, whatever techniques being used right now for Vestamid Care, the same techniques can be used for bondable Vestamid Care. So steam sterilization,
Mhm.
ETO, gamma, I mean, you name it, the same techniques can be used for sterilization.
Okay. Basker, that the speaking of the Vestamid series, the ML21, the nylon 12 is very popular in minimally invasive
Yes.
devices and in extrusion for balloons and also for the we talked about the proximal end of a catheter shaft. And I know it's not listed yet, but has there been any work or are there any plans to make a bondable ML21?
The same chemistry modification can be done for the nylon 12 products, the ML21, ML24. So we have some ongoing discussions on that. Right now, in the past few years, our focus has been on the elastomer part, which is the PEBA. So that's why we came up with MEB grades. So the next focus will be on the ML grades. So yes, so we have some ongoing activities on that.
Okay, good. I think people would be interested in that. If Basker, if I put my extrusion cap on, which it's always on, thinking of the future and extrusion technologies related to the structure of the EFEP and the bondable PEBA, one of the gold standards in medical extrusion, it's variable durometer extrusion, where
Yes.
on the fly you're changing the durometers, let's say 70D to 40D, for instance.
Yep.
And I envision in an application like this, using these two materials, that you could co-extrude the inner EFEP at a constant wall thickness, and then vary the outside jacket PEBA from, for instance, 71D to 40D. I don't think that's been done before, but there's a lot of smart extrusion folks out there, and I think the wheels might be spinning in their avenue as well, maybe to think of something like that. I think that would be a very applicable and unique design to be able to co-extrude those materials in that way in a variable durometer fashion.
Yeah, it's the VESTAMID Care product is a very versatile product. It's flexible. It's got kink resistance. The backbone chemically of the VESTAMID Care bonding version is not very different from the VESTAMID Care product. And so, whatever technology is being used right now, when it comes to making a catheter that varies in the hardness level, going from a nylon 12. Let's say nylon 12 is typically in the 75 SHOD range, and making it softer and softer towards the distal end, 62, 55, 40. Whatever techniques is being used right now, same can be used for bonding grades of VESTAMID Care. So we're very proud of this technology. Same machines can be used, same process conditions can be used. So you're not changing much. The chemistry modification was done mainly for the fluoropolymers, or adhesion with fluoropolymers, I should say.
Okay. Well, very interesting. I think this is a winner, and I think people will find that as well if it's used more often and people try it out, especially in the early stage. And that's why I was asking about maybe samples and things like that. And sounds like you have that covered as well. So very good.
Yeah,
very interesting conversation.
We have resin samples, we have catheter samples. So please do let us know if anyone is interested. Products are commercial, and like I mentioned before, a very major global company has already tested this. They love the product, and we're actually planning on doing some more trials with them. Thinner version of the catheters. So we're pretty excited. This is going to make a huge impact in the multi-layer catheter industry. And
absolutely
looking forward to what else is out there.
Excellent. Well, hey, Basker, thanks so much for sharing that the experience and the work that you've done so far. And I think there's a bright future with this combination. So good luck.
Yeah, thank you, Steve. Thanks for having me on the podcast, and thanks for the opportunity.
Thank you for listening to MedX, the Medical Extrusion Podcast, presented by US Extruders. Please subscribe to make sure you're getting the latest episodes. For video episodes, go to us-extruders.com/podcasts. All links are available in the show notes.